Can you believe it? We've made it to the last unit of AP Physics. We're going to be doing simple harmonic motion, periodic motion, and oscillatory motion. This is the first lecture where I want to introduce you guys to periodicity. So what is periodicity? Well, the root word here is period, and so we have some experience with things that have periods. For instance, when we talked about universal gravitation and satellite motion. A good definition of periodic is repeating predictably. And that means two things are true. Something that moves periodically follows the same path over and over, and it takes the same amount of time to complete that path every time the object does it. Let's look at some examples of different things that behave periodically. Here's the Bay of Fundy and its tides.
Wave. As the water in the Bay of Fundy ebbs and flows, it creates a phenomenon that occurs nowhere else on the planet. Located on the east coast of Canada and resting on the coastlines of the provinces of New Brunswick and Nova Scotia and the American state of Maine, the Bay of Fundy stretches 180 miles long, and the mouth of the bay is 62 miles wide, with its depth ranging between 400 and 700 feet. The tides of the Bay of Fundy are so dramatic that they are considered the highest tides in the world.
The tides of the Bay of Fundy are so dramatic that they are considered the highest tides in the world.
So that's one example of something that behaves in a periodic fashion. These tides go up and then go back down over the same path and in the same regular repeating time interval. Let's look at another example. This is actually a recreation of a classic experiment, Foucault's pendulum. This is at the Chicago Museum of Science and Industry.
Oh, got it! Oh! Not yet, but soon. Oh, got it!
So this pendulum is another example of motion that repeats in a predictable fashion. And we can use examples like the pendulum, which we'll do in a moment, to try to derive some mathematical understanding of how periodic motion functions. Alright, one last example. This is just some guy on YouTube I found, and he decided to make an animation of something that doesn't exist. This is if planets had orbits that corresponded to the Fibonacci sequence, but it's kind of cool. So circular motion and orbital motion are good examples of periodicity. So hopefully you get the idea now. All of these examples have one thing in common. They repeat in a predictable fashion. That's what periodicity means. That's what periodic motion depends upon. Let's introduce some of the terms that you'll need to be familiar with for this unit. Equilibrium refers to the natural resting location of an oscillating system, sort of its center. Oscillation means one complete cycle. You may have oscillating fans at your house that go left to right, left to right. That would be one cycle, would be all the way from left to right and back. So oscillatory motion is like these fans. Amplitude is the maximum displacement from equilibrium in either direction for an oscillating object. So with the example of your fan, if your fan is pointing straight forwards, it's going to go a certain distance to the left, then stop, and then turn back to the right, pass its starting position, and go more to the right than it began, and then stop, and finally turn left and return. That would be one oscillation, and the maximum turn distance would be its amplitude. Period tells us how long does it take for a system to complete one oscillation, and frequency is how many oscillations are completed per unit time. Most common unit of time is seconds. How many times does an oscillation happen in 1 second? So here's how I sort of think of these things. It kind of helps me. Equilibrium is like your home position. Oscillation is a business trip, or really just any trip. You're going to go somewhere and then you're going to come home. Amplitude would be how far you'll ever be from home. Your period is how long are you going to be gone before you take off for another trip. So what is the time for one full trip before another one begins? And then frequency is how often will you return to home? How often will you pass through the starting point? let's try to make sense of these terms. I want to start with the example of a pendulum. And let's just first watch a pendulum in terribly animated motion because I'm not very good at PowerPoint. Oh man, that was fantastic. So as a pendulum swings, assuming it started at rest here at the top position on the left-hand side, I want us to identify those 5 new terms as they apply to this motion. Alright, so here you have all the different positions at once, so we can refer to them and try to identify these terms. We'll start with the top 2, equilibrium and oscillation. Equilibrium, remember, is sort of the natural resting place of an oscillating system, and so for a pendulum, it's right down the center. If the pendulum was put there, it wouldn't naturally start swinging, it would just stay there. That's it, sort of where it wants to be. Oscillation refers to one complete cycle or trip. So let's see if we can figure out what that would mean. Starting from the bottom this time, and I'm going to imagine that I gave it some little push to the right, it's going to swing up to the maximum height shown, then back down to its equilibrium position. That would be a tempting answer. This is an oscillation, up to the peak and then back to the starting point. It's incorrect because this hasn't yet completed a full cycle. It's going to go up to the top on the left side again, well, for the first time, but the top again, and then it's going to return to the bottom. This is a complete cycle, and so a good way to remember if you're ever confused is if you complete one oscillation, you've seen everything on your trip twice. See if we can't figure out the amplitude of this. Amplitude is, again, the maximum displacement from your equilibrium position, which is that dotted line down the center, the black line. So there's 2 of those. One is on the left here. That's the highest it ever gets, or the farthest from center. And one's on the right. That is not coincidental. Amplitude is always achieved twice, as long as you're talking about a system that oscillates without friction. So it's going to achieve the same height on both sides. That's true for not only pendulums, but all periodic motion. And one of the amplitudes is always positive and the other is negative, depending on how you define direction. How do we want to measure it? That's the problem here. So we could sort of measure it linearly, like the distance. Get your tape measure out and go from the bottom to those apexes. You could measure it sort of horizontal distance. You could measure it vertical distance. The problem with all 3 of those is that they're all dependent upon the length of the string. And so we want a measurement that would work for any string length, an amplitude that could be reported regardless of whether or not we knew the string length. And to do that, we're going to use an angular measurement, and we'll call this theta. So the maximum displacement for a pendulum is theta max, the displacement angularly from its equilibrium position. And that's the same on both sides because of what we said over here, that amplitude is achieved twice, once positively and once negatively, and those are equal in magnitude. Amplitude is equal in magnitude in both directions. Finally, we could try to identify the period and the frequency of this pendulum. So it's going to start on the left this time. I know the last example started at the bottom, but we'll go back to the left. So if it starts over here, it'll first swing over until it comes instantaneously to rest on the right side, and then it's going to swing back. And that would be one full oscillation. It satisfies our requirement that you've seen everything twice. And because you've made it back to your starting place, you would just need to time that. However much time it takes to complete that trip would be your period.
So I'm going to do the timing from the highest point over here. So ready, from the highest point over here. 0, 1. Set, 0, 1.
So you see she was measuring it at its apex on the right side. You don't have to start at the top of its motion. You can measure period between any 2 corresponding spots in an oscillating object's path. So for instance, you could have started the stopwatch where the object is pictured here, sort of at the bottom, as long as you stopped the stopwatch when it got back to that spot. It's the same amount of time between any spot you want to start and end your timer at. Alright, I want to try to make sense of the relationship between a period and a frequency for an oscillating object. We're going to make this a little bit less scientific, but I think the analogy is helpful. Period is, if you imagine visiting somebody, it's how often you go between visits. Like, well, how much time passes from one time till the next time you visit. Frequency is sort of the opposite. It's not how much time passes, it's how often do you visit. So in a given length of time, how many visits do you make? Therefore, a good example would be, imagine a child that visits their parents every 6 months. So over the course of a year, what is their period and what is their frequency? Go ahead, pause the video now and see if you can figure out both of these. The period of the visits would be half a year. So again, going back to the definition above, how long between visits from one visit to the next is 6 months or half a year. What's the frequency of the visits though? How many visits do I make per unit time? Well, that would be 2 visits per year. And you notice there's an interesting mathematical relationship between these two numbers. Can you spot it? They're reciprocals. Period is defined as 1 over the frequency, or the reciprocal of frequency, and then you can rearrange this and algebraically manipulate it to get the frequency is 1 divided by the period. So they are inversely proportional, and if you know one period or frequency, you can find the other. All right, one last example here. Let's look at a mass on a spring on a frictionless surface. Notice my note over here. What we want to do here is first identify the equilibrium position. So let's assume that we're not touching the block, but it's attached to that spring, and then the spring on the left side is attached to this purple wall. And we're not going to compress the spring or stretch it. And because we haven't stretched or compressed the spring, there is no motion. That means the spring is sort of at its natural favorite distance, which we call equilibrium. So right here, we'll say is x equals 0, or its equilibrium position. Then I'm going to compress the spring some distance to the left, d. Okay, now we have a compressed spring. The block has moved some distance d to the left. Let's try to apply the terms that we were just introduced to. This position, assuming I don't compress it any further, this would be x equals negative d, right? That's the distance d that I compressed the spring. What would happen then if I let go of the spring? And remember, again, there's no friction. Well, I think it's pretty obvious. It's going to be pushed to the right. The spring is going to exert this restoring force, trying to get back to its equilibrium position. But while the block moves towards x equals 0, or equilibrium, it's going to be accelerating. And then it's not going to just stop instantaneously at the center, at the equilibrium position. Instead, it's going to pass that because it has so much velocity, and the spring won't like that either. The spring will then start pulling left, pulling backwards towards the equilibrium position. So what I want to figure out is how far past x equals 0 will this block go, assuming there's no friction or air resistance to slow it down. And the answer, you probably could guess, is without any friction to take energy out of the system, the block will go to the same distance right of equilibrium that it was initially compressed left of equilibrium, or d. It's going to again go to d. Then the block, assuming we don't interfere, will oscillate back and forth between negative d and positive d, and that means its greatest displacement from its equilibrium position is this distance d. So we have a new term that we can use instead of distance d. Maximum displacement is amplitude. So here we have the amplitude of the block in both directions, and as we said earlier, one of them is negative, one of them is positive, but they are equal in magnitude. They're the same distance from equilibrium. Let's try to make sense of the other new terms as they apply to this block on spring system. We've already talked about its equilibrium position and then its amplitude. So what would be a complete oscillation starting from the center here at equilibrium? Imagine you give it just a little tap to the left, just a real quick tap. It's going to then move to the right as the spring continues to resist its motion, and then it's going to stop at its maximum compression or at its amplitude. It'll then move back towards center, but just like with the pendulum, that's not an oscillation because you haven't seen everything on your trip yet. Remember, for any oscillation to be complete, you need to see everything twice, or the block does. So it's going to then continue to the right past equilibrium, reaching its amplitude in the positive direction, stop instantaneously, and then come back to equilibrium, and at that point it has completed an oscillation. What about the period? Period is, again, the time it takes to complete an oscillation. So we just said what an oscillation was, or what constitutes a complete revolution here. So let's just say it's the time for that to happen. It's the time, starting from center again, to go over to the left, back to center, back to the amplitude on the right, and then back to center again. You got your stopwatch out, timed it, that is your period. And finally, if you know the period, if you measured it on a stopwatch, it's easy to find the frequency. You just take 1 and divide it by the period. They are reciprocals of each other.